Welcome back to this next video in which we are discussing coordinate vectors with respect to a basis. Okay, so in the previous video what we saw is that if you're working in a finite dimensional vector space, what you can do is use a basis of that finite dimensional vector space to write all the vectors of the vector space as a unique linear combination of the basis vectors. So some c1 v1 plus c2 v2 plus all the way up to cn vn. And you can do this for absolutely all of the vectors, and all of the vectors have a unique linear combination in terms of the basis vectors. Okay, so what this then allows you to do is associate with every vector of the vector space a coordinate vector with respect to that basis. Okay, now this is very useful because the vector space previously was a very abstract object. The symbols could have been stupid squiggles like this. Now, however, what we can do is associate something sensible, an n-tuple of elements of the field with each one of the vectors. Okay, and where are we going to get these elements of the field? Well, they are going to be the scalar coefficients that you have to put in front of the basis vectors to get the correct linear combination which gives you that vector. Okay, so each vector in the vector space then can be associated with a coordinate vector, and this gives us a nice new symbol for all of the vectors of the vector space. Right, but it gets better than that, because if you add two vectors together in the vector space, then the coordinate vector of the addition of the two, okay, so the answer to this is going to just be all of the coordinates of the two original vectors that you wanted to add together, added together in the field. Okay, so this reduces addition in the vector space down into addition in the field, okay, where we just add the coordinates in the field. Okay, so that's lovely. Again, we've taken something that's very abstract down into something that's more concrete. We've taken it from vector spaces into field theory. Okay, and similarly, scalar multiplication is lovely as well. Okay, if we want to scalar multiply any vector in the vector space by a scalar in the field C, then all we need to do is find the coordinate vector for that vector v with respect to this basis, and then all we need to do is multiply all of the coordinates by this scalar c, where that's a multiplication that's done in the field. So again, it's reduced scalar multiplication in the vector space to multiplication in the field. It's reduced it to a problem in field theory. Okay, so this gives us a beautiful hold then on vector spaces. Okay, right. Now, there are two things that I want to dwell on more now in this next video. The first is the fact that we have now actually set up an isomorphism between our vector space and a vector space of the form Fn. Okay, and this means that actually we've succeeded in characterizing all finite dimensional vector spaces, okay, and hugely simplified the topic. So that's the first thing that I want to discuss. The second thing that I want to go into in more detail is the fact that there is no right basis to use as the basis to write all the other vectors of the vector space as coordinate vectors with respect to. Okay, and I want to destroy your idea that there is a right basis to use, and we'll go to R2, which is the ultimate easy example where everyone thinks there is a right basis to use, but I want to show you or try and persuade you that there is not, and that is such an important concept. Okay, so firstly then, let me deal with this isomorphism. Okay, so we have now succeeded in attaching to all of the vectors in our abstract vector space, capital V over the field capital F, these coordinate vectors. But these are symbols that we used in another vector space. Okay, so in the video on the definition of a vector space, we saw that certain vector spaces that you can always build for any field capital F are the vector spaces Fn. Okay, now these are the vector spaces where you take all n-tuples of elements of the field, and you can either arrange them in a column or you can arrange them in a row. Since we've got these as columns, we might as well have them in columns. It really doesn't matter at this stage. So x1, x2, all the way down to xn, like so, where the xi's are elements of your field, capital F. Okay, so this is the set that you construct when you're trying to construct this vector space. You create this great big set of symbols, and then if you want to turn it into a vector space, what you have to do is define an addition law that obeys the properties of an abelian group, and a scalar multiplication law that obeys the axioms that we want scalar multiplication to obey for a vector space. Okay, and the way that we define addition on this is if we have two vectors, so x1, x2, all the way down to xn, and another one here, x bar 1, x bar 2, all the way down to x bar n. So these are just two vectors from this vector space to B, and the way I'm going to define addition here is the addition of this symbol with this symbol. I'm going to define it in terms of addition in the field. Okay, so I'm just going to add the components here in these symbols. Okay, so I'll add x1 to x bar 1, I'll add x2 to x bar 2, okay, and I'll go all the way down until I add xn to x bar n, like so, and that then will give me another element of this set, because whenever I add two elements of the field together in the field, I will end up with another element in the field. Okay, so we still will end up with an n-tuple of elements in the field. So that's how I'll define addition, and indeed this addition law does obey the axioms of being an abelian group, so this is looking good. Then what we'll do is define scalar multiplication. So if I want to take some element of the field, I almost said some real number, but we are working in an abstract field here. Okay, so if you take some element of the field and you want to scalar multiply it by a vector from our vector space to B here, x1, x2, all the way down to xn, the way I will define this is in terms of multiplication in the field. So I'll just multiply all of the components in this symbol by C in the field. So I'll do cx1, cx2, all the way down to cxn. Okay, and indeed, amazingly, this scalar multiplication law does actually obey the axioms that scalar multiplication needs to obey for this to be a vector space. Okay, and indeed, all of these answers here that I'll get will be elements of the field, so indeed, this will be another symbol back within this set. Okay, so that's the definition then of Fn. You create these symbols, you define an addition and a scalar multiplication on it like this, and it does obey the axioms of a vector space. What I have now shown is that any abstract finite dimensional vector space is isomorphic to one of these. Okay, and quite simply the way that you can do this is you've established an isomorphism already. You're just going to map all vectors onto their coordinate vectors. So I suppose I should just remind you from group theory of the concept of an isomorphism, because at no point so far have we actually discussed the concept of an isomorphism for vector spaces yet. Okay, so I'm assuming you're familiar with group theory. Now in group theory, an isomorphism, which we'll denote as phi here, is a mapping from one group to another group that relabels the elements of one group with the elements of another group, and it basically turns one group into another. Okay, so if you relabel up the composition law in one group, it turns it into the composition law in the other group. Okay, so it's the concept that the two structures are actually the same. All that you've done is use different symbols potentially, okay, and the isomorphism is then the relabeling map that can relabel up one of your algebraic structures and turn it into the other algebraic structure. Okay, so what I'm going to do then is show you that we have an isomorphism between our abstract finite dimensional vector space over the field F and our vector space that we've got defined here, Fn, where the n here will just be the dimension of the vector space V. Okay, and it shouldn't have that little bar there, it should just be an arrow. Okay, right, so an isomorphism of two vector spaces then, generalizing from group theory, this is going to be a relabeling map that's going to relabel the elements of this vector space with the elements of this vector space. And the idea is then that if you relabel up the composition laws of this vector space, okay, so what I mean by that is go through this addition composition table, and wherever you see a symbol in this set here, replace it with the symbol in this set here that it's been mapped onto. Okay, so if you relabel up our addition composition table according to the isomorphism, the relabeling map, and you do the same thing for the scalar multiplication here, so you relabel up scalar multiplication according to our relabeling isomorphism map, then it will turn this addition and this scalar multiplication table into the addition and scalar multiplication tables in this vector space Fn. Okay, and hopefully that should be pretty obvious just from what I've shown you here, that is going to be possible here. Okay, so the way then that I'm going to define this isomorphism is it's just going to take any abstract vector in my vector space capital V, which could have some ridiculously silly symbol, and it's just going to take it to its coordinate vector. Okay, so I'll just write this out, C1, C2, all the way down to Cn, like so. So that is indeed a relabeling map. Okay, it will be a bijective map. Okay, so all vectors in here will be given a single vector in the codomain vector space here. In addition, every vector here will have a single vector back here that was sent onto it. Okay, because all of them do represent a linear combination, which will be some vector in our vector space here. And in addition, we know that linear combinations are unique, which will mean that each vector will only have one of these being actually ascribed to it. Okay, so this is a well-defined map, and it is actually going to obey the properties of being an isomorphism, because what we know is that if we do just relabel up our addition composition law with the coordinate vectors, we know exactly how that works. Okay, we know that if you add any two vectors together in terms of the coordinate vector, the answer is this here. Okay, and in addition, scalar multiplication, if you relabel up the scalar multiplication law, the answer to any vector here, scalar multiplied by an element of the field, is this. And of course that's the exact addition and scalar multiplication composition laws that we have in this vector space. So I hope it is kind of obvious that if you relabel up the vectors in this vector space with the symbols in this vector space, that the addition composition law in this vector space is being turned into the addition composition law here. It's the same addition composition law, and if you relabel up the vectors in here with the vectors in here, the scalar multiplication law also becomes the scalar multiplication law in here. Okay, so what this then shows us is that any vector space, any finite dimensional vector space, is isomorphic to a vector space of this form Fn. Okay, so if you've got a finite dimensional vector space over the field capital F, it will be isomorphic to the vector space Fn, where this n is going to be the dimension of your abstract vector space capital V. So what that means is that really we have completely characterized finite dimensional vector spaces now. They are all of this form. Okay, we do not get any more truth from studying this one than we would get from studying this one. Okay, all that's different is the symbols. The symbols might be more complicated over here, but the symbols are meaningless. Okay, what's important is the actual algebraic structure, and the algebraic structure is exactly the same over here. Okay, so we now have completely characterized all of the finite dimensional vector spaces, and that's beautiful because we know that these ones here are incredibly simple to understand. Okay, now another important point is that you could do this for loads of different bases. Okay, we took a certain basis of our finite dimensional vector space and we wrote all of the vectors in that finite dimensional vector space as coordinate vectors. Okay, and now we've established this isomorphism where we're mapping the vectors in our abstract vector space onto the coordinate vectors in our vector space Fn. But you could have used a different basis. If you'd had a different basis, you could have used that one as well. And that one would have ascribed very different coordinates to all of the vectors of the vector space. Okay, because remember, the coordinates are just the linear combinations of the basis vectors that make each of the vectors in the vector space. Okay, so what that tells us is that there is actually loads of different possible isomorphisms of this finite dimensional vector space onto the vector space Fn. Okay, and that tells you something about the incredible symmetry that vector spaces have. Okay, because if I'm saying that there are different ways that you can relabel up this vector space and turn it into this one, okay, different equivalences, then what that means is that there are loads of mappings of the vector space onto itself which preserve the addition and scalar multiplication laws. There are loads of automorphisms. There are loads of ways of relabeling up the elements of the vector space with elements of the vector space itself. Now I'll write this explicitly out. There are mappings phi which map the elements of the vector space, and I put that bar again there again, okay? There are loads of mappings phi which map the elements of the vector space onto themselves, relabeling maps where you relabel up the vector space elements with other elements in the vector space. So a reshuffle about basically in the vector space, such that when you do this relabeling map, it doesn't actually change the addition or scalar multiplication composition laws at all. Okay, so if you do go through and relabel up the entire addition and entire scalar multiplication composition tables, all of the actual answers to what two elements of the vector space multiplied together or added together or scalar multiplied by any element of the field is actually going to be the same. Okay, so that's incredible. That tells us about incredible algebraic symmetries in the structure of vector spaces. Okay, so vector spaces are quite incredible for the number of algebraic symmetries they have. Indeed, any two different bases that you have defines an automorphism of the vector space onto itself. So these are incredibly symmetrical algebraic structures. Okay, right. So the final thing then that I want to do in this video is stress this point that there is no right basis and there is no wrong basis. And to do this, I want to use an example which people are very familiar with and which people are used to thinking about there being a right basis for. Okay, and that example is going to be R2. So a nice simple example. Okay, so I'll firstly actually give you the abstract definition of R2, and then we'll discuss the fact that there is no right or wrong basis. Okay, so R2, I'll firstly remind you of the definition of it then. So R2 is one of these Fn vector spaces, just where F, the field, is the real numbers specifically. So it's going to contain all pairs of real numbers, like so, x1, x2. So these xi's are elements of the real numbers. So you take every possible pair of real numbers, you stick all of them in this column vector form into this great big set. That's the set that underlies R2. Okay, and then for an addition law on this vector space, what we will have is the old favourite, exactly as we had it here. Okay, so to add one vector x1, x2 to another vector x bar 1, x bar 2, all you will do is add the components in these symbols together. So you'll add the x1 here to x bar 1, where this is now addition in the real numbers, okay, and you'll add x2 to x bar 2, again where this is now addition in the real numbers. Okay, so that's the way we define addition then on this vector space R2, and of course scalar multiplication. If I want to multiply any vector in here by a scalar c from the real numbers, the way I do it is just multiply all of the components in this symbol by the real number c in the real numbers. So I'll do c times x1 where this is multiplication in the real numbers, and I'll do c times x2 again where this is multiplication in the real numbers. So that's the way I'll define scalar multiplication in this vector space. Okay, so that then is the definition of R2. However, there is a nice way that we can gain intuition about R2. Okay, so there is a picture which people often visualize for R2 to help us understand this vector space. Okay, and I just want to draw that picture here. So what we can do is we can take this two-dimensional grid like so. Okay, I'll just draw the two-dimensional grid, and what we can do is we can associate with the points of this two-dimensional grid vectors in our vector space R2. Okay, so I won't draw too many of these lines, I'll just draw a few more. So here's my two-dimensional grid, here is the origin, well, where was the origin? There was the origin. Okay, and now what we can do is we can associate the vectors in this vector space of R2 with points on this grid. And the normal way that people do this, but by far not the only way, is to associate this unit point here, over here, like so, which is a unit away, with the vector 1, 0 in your vector space. So we usually associate that with 1, 0. So this little arrow here to that point from the origin will be associated with 1, 0. Okay, and then we will associate this little arrow here to this point up here with the vector 0, 1 from our abstract set over here. Okay, and then if we want to associate all the other vectors of R2 with points on this grid, or with the position vectors of points on this grid from the origin, so with these little arrows, what we do is if we have a vector x1, x2, all we do is go x1 along in this grid, x2 up in this grid, and then it will be the position vector. It will be associated with the arrow to that point from the origin here. Okay, and what's absolutely beautiful about this, why we do this, is because it gives us a very intuitive picture of what it means to add two vectors together in R2 and also scalar multiply a vector in R2 by an element of the real numbers. Okay, so just drawing a picture for this, if we have one vector here, okay, so this is obviously the arrow that will be associated with the vector 3, 1, okay, so I will colour this in green here, so here is 1, okay, and if I have another vector, okay, so this little arrow here will be the one associated with negative 2, like so, negative 1, 2, and I'll colour that in purple here. Then if we want to add these two vectors together in our vector space over here, a way of visualising that through this picture, what it means in terms of this picture is bring this purple arrow here to the tip of the green arrow, like so, and then go from the origin to that final point there, and then this new position vector that you've got here, that will be the position vector associated with the answer to these two added together in the abstract field, in the abstract vector space here. So if I add them together in the abstract vector space, of course what I'll end up with is adding 3 to negative 1, so I'll get 2, and then I'll add 2 to 1, so I'll get 3. So the answer here would be 2, 3, and indeed you can see that the answer in terms of the picture here is the position vector that will be associated with 2, 3. Okay, so addition has that very beautiful interpretation in terms of the picture. In addition, scalar multiplication has a beautiful interpretation in terms of the picture. If you want to, for instance, scalar multiply a vector by 2, what you'll end up doing in terms of the picture is doubling the length of the vector but keeping it in the same direction. Okay, so scalar multiplication and addition have beautiful interpretations in terms of this picture, and that's the reason that we associate with these abstract symbols these position vectors on this grid. Okay, so the basis that people think is the most natural basis to use for R2 is what's called the standard basis. Okay, and I'll put this over here. So the standard basis is called E because it's considered special, okay, and it's the set that contains the two vectors which are 1, 0 and 0, 1, i.e. the two vectors that we associated with this position vector here and this position vector here. Okay, that is considered the standard basis of R2. However, there is absolutely nothing special about it at all. You can take a different basis of R2 and it is just as good as this basis. There is literally nothing good about this whatsoever. It is a basis, I won't deny it that, but it is not special, it is not better than any other basis, and people tend to think it is. So the first argument as to why you might think that this basis is better than some other basis is because look at these. These are beautifully simple. Okay, if I want to write any vector, okay, if I want to write any vector in R2, x1, x2, in terms of a linear combination of these bases, these basis vectors, then it is just going to equal x1 times that first one, 1, 0, plus x2 times 0, 1. Isn't that absolutely wonderful? How can you deny that that is a fantastic choice of a basis? Okay, well, you are deluded and you're being tricked by the fact that all that's special about this choice of a basis is the symbols. Okay, these vectors here that I've put into this basis, they are only considered special. You are only thinking that they are special because they have very beautiful symbols. They have this beautiful symbol, 1 as the first component and 0 as the second component, and 0 as the first component in this one's case, and 1 as the second component in that one's case. Okay, so the symbols are all that's special here. The symbols have absolutely nothing to do with the algebraic structure. The algebraic structure is this abstract addition and the abstract scalar multiplication. Okay, you can change the symbols. You could change these to whatever you like. Okay, that doesn't matter. The symbols are not important. Okay, and you might say, but look at this relation. This is at the algebra, this is a scalar multiplication, this is addition, but the only reason that you think that's a nice relation is because it makes this symbol here. Okay, so this argument of why this is special is just about the symbols, and the symbols are not important. Okay, people's second argument as to why this is the most natural basis is then, but these two are perpendicular to each other and of unit length. Okay, this is just an abstract algebraic structure. R2 is an abstract algebraic structure. There is absolutely no notion of what the length of a vector is or what it means for two vectors to be perpendicular defined on this yet. I have not defined that. All that it is a set of symbols with the ability to add them together and scalar multiply them. That's all that I've defined at the moment. Okay, we have associated them with these position vectors on this picture, and that is now tricking you because the structure on this picture has the concepts of length and perpendicular. Okay, but this abstract algebraic structure, which is the real R2, this isn't the real R2, this is the real R2. This has no notions of what it means for what the length of a vector means or what it means for two vectors to be perpendicular. Okay, I haven't defined that. You can define that if you want, but I haven't defined that, and it's not an algebraic property. Okay, so the argument of them being perpendicular to one another is purely, again, man-made. It had to do with the way that I chose to associate the elements of this set with the position vectors on this picture. And why did I choose to associate this vector with this one here and this vector with this one here? Well, not that one, but this one here with this one here. Okay, I chose to use those simply because their symbols were nice. Okay, so again it comes back to the argument that their symbols are nice, but the symbols are not important. You can change the symbols. The algebraic structure is what's important. That's what we're trying to study. Okay, so to absolutely make this clear, what I want to do is show you that I could use another basis of R2. Okay, I could associate these other basis vectors with these nice unit length position vectors which are orthogonal to one another, and then I could associate all other vectors with vectors on this grid according to their coordinates with respect to that second basis, and addition and scalar multiplication would still obey the beautiful intuitive pictorial sense that I've got here. Okay, so let me do this now. Oh, and I've used that slide. So let me show you now another basis then for R2. Okay, so I'm going to take a basis that people often use when they're trying to show a counterexample of another basis. Okay, so here comes my other basis that I'm going to use of R2. Okay, so it's going to contain two vectors. One of them is going to be 2, 1, okay, and the other is going to be 1, 2. Okay, so in terms of our previous picture, the previous way that we were doing this, these vectors look like this on this picture. Okay, so 2, 1 would be this one if we're using this association that we've had previously, and 1, 2 would be this one if we were using the same association as we had previously. Okay, so I want to firstly prove that these two vectors do actually form a basis of R2, so I want to prove that they together span the entire of R2, and I also want to prove that they are linearly independent. And then what I want to show you is that I could associate the vectors of my vector space R2 with the position vectors of that grid in a different way and still have it so that the addition of vectors in my abstract vector space can be interpreted as in that beautiful pictorial sense on the grid, and scalar multiplication in the abstract vector space can still be interpreted as the beautiful pictorial sense on the grid. Okay, and then hopefully I will convince you that there really is nothing special about the standard basis of R2, or indeed of Fn more generally. Okay, right. So, firstly then, let me show you that this is a basis. So I want to firstly show you that this spans the entire of R2. So what I want to consider is a linear combination of these two vectors. So C1 times the vector 2, 1 plus C2 times the vector 1, 2. And I want to try and prove that if I have an arbitrary vector in R2, which is something of the form x1, x2, so this is my arbitrary element of R2, I want to prove that I can find C1 and C2 such that if I use that linear combination of these two basis vectors, I will get this vector x1, x2. So I'd quite like to find then the coordinates of x1, x2 with respect to this basis. Okay, so let's try and do this. So firstly, let's work out what C1 times this vector plus C2 times this vector is, because we know how scalar multiplication and addition works within our vector space. Okay, so C1 times this will just equal 2 times C1 and then 1 times C1 underneath there, and then we'll have plus C2 times this will give us C2, and then we'll end up with 2 times C2 down here. Now when we add those two together in the vector space, what we'll get is 2C1 plus C2 and then underneath C1 plus 2C2, where all of the multiplications and additions here are done in the field of real numbers. Okay, so a very intuitive field to be working in. Okay, so what we now want to know is if we've got this vector x1, x2, can I find C1 and C2 such that 2 times C1 plus C2 is going to equal x1, and C1 plus 2C2 will equal x2. Now remember, the x1 and x2 are the knowns. Okay, C1 and C2 are the variables. We are trying to find solutions C1 and C2 such that both of those two simultaneous equations are satisfied. Okay, so this is a simple exercise in GCSE maths. Okay, so now what I'm going to do is I'm going to do it by substitution. So I will rearrange this one to get an explicit formula for C2. So I can rearrange this to say that C2 will equal x1 minus 2C1. And then I'm going to substitute in this expression for C2 down here. Okay, so what I'll end up with then is C1 plus 2 times x1 minus 2 times C1 is equal to x2. And now just expand this out. C1 plus 2 times x1 minus 4C1 is equal to x2. And then what I'll end up with is negative 3C1 is equal to, take this onto the other side, and I'll end up with negative x2 minus 2x1. Okay, and then what we want to do is just divide through by negative 3. So I'll end up with C1 is equal to 2/3 x1 minus 1/3 x2. Okay, so there's my expression for C1, and now all I need to do is plug this expression for C1 back in here to get my expression for C2. So now I'll get that C2 is equal to x1 minus 2 times C1. So I'll put in 2/3 x1 minus 1/3 x2, like so. And now if I expand this out, I'll get that it's equal to x1 minus 4/3 x1. So of course that will give me minus 1/3 x1. Okay, and then I'll get minus 2 times minus 1/3 x2, but of course that will give me plus 2/3 x2, like so. Okay, so there's my expression for C2. So you give me an x1 and x2, and you are challenging me to find C1 and C2 such that this linear combination of these two vectors will give me this vector in R2. I have now found you the C1 and C2. Okay, so these are effectively the coordinates of the vector x1, x2 relative to this basis containing the vector 2, 1 and 1, 2. Okay, so I can indeed then get any vector in the vector space R2 by taking a linear combination of the vectors in this set. Now, why is it going to be linearly independent? Well, I need to show that the only linear combination of these two vectors that will give the 0 vector then is going to actually be the case where C1 and C2 are both equal to 0, so the trivial linear combination. So if I want this to equal the 0 vector, then I want x1 and x2 to equal 0, so just stick in x1 and x2 is equal to 0 here, and of course you'll get that C1 and C2 have to also equal 0. So therefore, we have proven that the only linear combination of these two vectors which will give the 0 vector is indeed the trivial linear combination. So basically, any vector x1, x2, which is an element of R2, okay, so this is just a symbol in R2, its coordinates relative to this new basis will be 2/3 x1 minus 1/3 x2, and then its second coordinate will be -1/3 x1 plus 2/3 x2. So this is its new coordinate with respect to this new basis. Okay, right. Now what I want to show you is that if I associate the vectors of R2 with that two-dimensional grid in a different way, it will work just as well as it did when I associated the vectors 1, 0 and 0, 1 with the two orthogonal unit vectors. Okay, so what I'm now going to do is draw my grid out again. Okay, so here is my grid once again, my two-dimensional grid. And this time what I'm going to do is I'm going to associate my two basis vectors with this new basis with the orthogonal vectors of unit length. So here's the origin, and now what I'm going to do is I'm going to associate this point here and this position vector to that point. So the one in turquoise here, I'm going to associate that with the vector 2, 1 from my vector space R2. Okay, and I'm going to associate this other point's position vector here, the orthogonal one, in orange here, with the vector 1, 2. Okay, like so. And then, the way that I'm going to associate any other vector of R2 with a position vector in this grid is I'm just going to take it to its coordinate vector here. Okay, so I'll go along the grid by this coordinate here, the first coordinate, and then I'll go up the grid by this coordinate here. Okay, and the beautiful thing here is that addition in the vector space of R2 can still be interpreted in that beautiful way, okay, because if I have two vectors, so let's have one vector here and one vector here, or rather these are the position vectors that they're associated with. If I want to add these two vectors together in the vector space, I know from my study now of coordinate vectors that, where is it? I can just add the coordinates together in the coordinate vectors and this will be my answer, okay? But when I add the coordinates in the coordinate vectors together, what that corresponds to doing in terms of the picture is exactly just putting this one on the end of this one like so, and then joining them up like that, okay? So what I'm trying to show you then is that with this different basis and this totally different way of associating the vectors of R2 with this two-dimensional grid, the beautiful interpretation of the algebraic structure in terms of the picture still holds true. Okay, so I hope now I have dissuaded you from the belief that there is something special about associating 1, 0 with this point's position vector and 0, 1 with this point's position vector. There is absolutely nothing special about that standard basis. Only the symbols are special. Okay, and indeed scalar multiplication also obeys the same beautiful picture interpretation, okay, because we know that if we have some vector and we're scalar multiplying it by some other vector, the way that we can interpret that in terms of the coordinate vectors is exactly just multiplying all of the coordinates by the scalar in the field, and as far as the picture is concerned, that the interpretation of that is just scaling the vector up or potentially flipping it round depending on whether it's a positive or negative number. Okay, so it really does not matter which basis you use. Whatever basis you use in your vector space, you can express the vectors as coordinate vectors with respect to that basis, and the addition of the vectors in the vector space can always be interpreted as just the addition of the coordinates for the coordinate vectors, and scalar multiplication can always be interpreted just as scalar multiplication of all the coordinates by that scalar in the field. Okay, and those beautiful ways of viewing addition and scalar multiplication are what give rise to this beautiful picture of what addition and scalar multiplication mean. So it really does not matter what basis you use for your vector space, okay? They are all absolutely equivalent. There is not one that is right and one that is wrong. The standard basis just has very nice symbols in the vector space Fn. Okay, and with that, I will end this video on coordinate vectors.